Welcome to ProjectSansar. In this tutorial, we would be dealing with the very basics of embedded programming. We would be taking a look at the ATmega 8 development board, the very basics of programming in embedded C, and by the end of this tutorial, you would be able to blink an LED based on an infrared input as a practical.
Now we will first go through all these sections of board one by one. First we have this 2-pin connector which is at the left top, which you can see here. Here we can connect a power source. Basically we can connect a battery of 9 volts. Remember that we cannot connect anything more than 12 volts and 500 milliampere. Also, to provide the power supply, we have a DC connector which is right at the top of this board. Here we can give the maximum of 12 volts. Now, if you come to this component, which is our 7805, which is a voltage regulator. Now, for the microcontroller supply, we need a 5 volt, which we cannot give straight away from the DC supply. So for that we need to convert the 9 volt or 12 volt supply to the 5 volts, and which is what this IC is doing, and the IC number is 7805. Now nearby to these ICs we have this switch, which is basically nothing but a power switch to turn on and off the power to the board. Now next to this particular IC we have some 2-pin connectors, as you can see here. These 2 pins are nothing but some power if you want to provide power to the external devices such as sensors or motors or anything else. So we have a plus 5 volt and the ground, which are 5 different types. Now as we need to program this microcontroller, we need to also have a USB connection by which we will be transferring the program from the controller, from the PC to our controller. And for that we have a USB connector which is right on the right side of the board, as mentioned here. So with this USB we can straight away program our microcontroller, and internally they are connected to the pins of our microcontroller, which we will be studying later on. Now coming to the microcontroller section. As you can see, this is our microcontroller. This microcontroller is being provided by AVR series. The name of the company which is manufacturing this microcontroller is ATmega. Now we will talk about the features of this microcontroller, and also we will talk about how we program this microcontroller. We will also see how we can transfer the data or program from the computer to our microcontroller. Now nearby this microcontroller we have a reset switch as shown here. Now this reset switch is basically to reset our microcontroller. Functionality of this reset pin is just to reset our microcontroller. Now nearby these reset switches we have a silver color component, which is nothing but a crystal oscillator, because our microcontrollers work on a frequency. So the main function of this crystal oscillator is to provide frequency to the microcontroller. And as you can see here, it's written on the left hand side of this crystal oscillator. It's a 12 megahertz crystal, so by which we are giving a 12 megahertz frequency to our microcontroller over here. Now nearby this microcontroller there are some pins which we have given for additional connectivity of different devices or different peripherals. Now nearby this controller we have these 3 connectors which we are used for connecting the sensors. So as you can see here, it has been mentioned as sensor 1, sensor 2 and sensor 3. Now coming down we have this IC, which is a 16-pin IC. The name of this IC is L293D, which is a motor driver IC. So by the help of this IC we can control 2 different motors with the help of the IC and the controller. Now nearby this motor IC we have these 4 different LEDs, which is basically used to give us an indication that something is working or not. As we all know that our LEDs are being used as an indicators for some things. So this basically is an overall view of our ATmega 8 board of AVR microcontroller. Okay, now first we will start with like how or what is a microcontroller, how the microcontroller is different from a microprocessors, and which are the different companies which are manufacturing controller and which are the different companies which are manufacturing processors. So first we will look at what is a microcontroller. A microcontroller is nothing but a small controller device which is basically processing or controlling some things with the help of some external or internal peripherals. It's also a decision-making device, as you can see on the slide. It's being a decision-making device used widely in embedded systems and intelligent devices. Now, as we all know today, the intelligent devices includes our smartphones, mobile phones, cameras, lots of different intelligent devices are coming. So all these devices use the technology called as embedded systems. All these embedded systems are having a microcontroller inside them by which we control a lot of different features of that particular device. So we will look at what basically a microcontroller contains inside it. You can see there's a central processing unit, what we call CPU. Now inside this chip we also have a memory, which we have a different kinds of memory such as our RAM memory, our ROM memory, our WPROM memories. We also have some external peripherals such as input-output registers. We have some ADC peripherals. We have some UART peripherals. We have some timers peripherals. UART, the acronym for UART is Universal Synchronous Asynchronous Receive Transmit. For ADC, it's analog to digital converter. Okay, so all these things comes under a single chip, and that is the biggest advantage of a microcontroller over a microprocessor. Like in microcontroller, we have all these peripherals embedded into a single chip, whereas in the case of microprocessors, these peripherals are built externally. That's the major difference between a microprocessor and a microcontroller. Now the second difference is, as we have seen here, as we can see on the slide, the memory inside the chip is been fixed. That means once this particular microcontroller is designed with a memory size of say 1 GB, it will remain for 1 GB for that particular microcontroller. But in the case of microprocessors, as we have the memory connected externally, so we can change the amount or size of the memory as per our requirements. So if you want, you can make it from 1 GB to 4 GBs or 8 GBs, or depending on what the requirement is. Now coming to the different manufacturers of processors and microcontrollers. Now in today's world, we have a different lot of companies which are designing or manufacturing this particular controller or a processors. The first one, of course, you all know, is Intel. Second one is AML. Third one is Samsung. Fourth one is Dell Semiconductors. Fifth one is Freescale Semiconductors. So these are some of the major companies which are basically designing controllers or processors. Now what we will look is to like what is this microcontroller. Okay, now here in this slide, as you can see, we are using microcontroller from AVR series of ATmega company. The name of this microcontroller is ATmega 8, and this is just a picture of what we are going to use as shown in the board as well. Now how this ATmega 8 got its name? Basically the the AVR implies to the ATmel family, or you can say the acronym for AVR is Advanced Virtual RISC. Advanced Virtual RISC, what you call as RISC. And this 8 in this particular name is nothing but the memory size of the flash, which is shown on the slide. It's an 8 kilobytes. So the memory size of our microcontroller is 8 KB. If it is increased to 16 KB, then we have 8mega 16. If we have 32, then we have 8mega 32, and so on. Now AVR is basically nothing but a modified Harvard architecture. Now coming to the architectural point of view, we have two different types of architectures. One is a Harvard architecture and another one is Van Neumann architecture. Now this AVR is basically a Harvard architecture with 8-bit RISC, which again stands for Reduced Instruction Set Computing. And it was developed in the year 1996 by ATmel Corporation. Now, whenever we use a microcontroller, there are some specialty or some features which are unique in that particular microcontroller. So what's special about this AVR? So first of all, of course, they are very fast. Second one, they execute more instructions in a single cycle. They are more faster than the PIC controllers, and also they consume less power. Now we will look into the different features of the controller which we are using right now. So our controller is ATmega 8. Now the first feature is it's a high performance 8-bit microcontroller. Now what do you mean by an 8-bit microcontroller? 8-bit means the data bus and the address bus of that particular microcontroller will have an 8-bit carrying capacity. That means in one transmission we can carry 8-bit of data through the data bus and 8-bit of address through the address bus. Now the second one is the ATmega 8 have a 16 MIPS of speed if running at 16 megahertz. That means the ATmega 8 has a processing speed of 1 MIPS at 1 megahertz. That means 1 million instructions per second can be executed at 1 megahertz frequency. The third one, that there are different registers which is inside our microcontroller for different communication between the peripherals and the controller. So we have a 32 into 8, which is 256 general purpose working registers. Now also we have the RC oscillator, which is an internal one. We also do have an external oscillator which is connected in our hardware board. Now coming to the last feature, which is the data retention. Now what do you mean by data retention? Data retention means ability of a device to hold or sustain the data within itself. That means the microcontroller can store the data inside them for 20 years if kept at 85 degrees Celsius, and can store the data for 100 years at room temperature, which is our 25 degrees Celsius. Now we will be coming to the memory segments of our microcontroller. Now as we all know that every controller or a processor will have a certain amount of memory inside them. Now there are 3 different memories which we require in every microcontroller. The first one is to be the flash, where we're gonna write or a program inside our memory. So that's called as flash memories, and the size of our flash memory in ATmega 8 is 8 kilobytes. It is programmable. Now the second segment comes is the EEPROM. The EEPROM stands for electrically erasable programmable read-only memory, and the size of our EEPROM is 512 bytes. And what's the difference between a EEPROM and a flash memory? Well, EEPROM, to erase the data we need an electrical signal, but whereas in the case of flash memories we do not need any kind of electrical signals, and that's why the flash memories have an advantage over WPROM memory. Now, whenever a controller starts executing any program, the first thing or the first code of which can code memory comes from the RAM, okay, which is a random access memory. So every controller will also have a certain RAM inside it. So the size of the RAM in our microcontroller is 1 kilobyte. So this was the memory segments of our microcontroller. Now we will be looking at the different packages in which the IC or the microcontroller is available in the market, and which type of packages are used in different industries. Now the first of this package is a PDIP package, which stands for Plastic Dual In-Line Package. Now the microcontroller which we are using, which is an ATmega 8, has 28 pin of PDIP, which is shown in this particular figure. So you can see why it's called PDIP package, because you can see one line is this one and the another one on the another side of the controller. So there are dual inline, and that's a package. And P, that stands for plastic, because it's made of a plastic material. So that's why we call this one as a PDIP package of microcontroller, which we can found in our board as well. Now, how do you recognize pin number 1 and the last pin of your microcontroller? Now, as you can see, there will be a notch on this particular microcontroller, and there will be a black dot on this particular side of the controller. Now, just the pin which is right next to that particular black dot, which is this one, is your pin number 1. And the pin which is just exactly opposite to this one will be the last pin of that particular controller, which is your pin number 28. And if you start from pin number 1, this will be 2, 3 and so on to 14. Now this one will be 15, 16, 17 and to pin number 28. Now the another package which we have, it's called TQFP package. The name of or the acronym for this one is Thin Quad Flat Package. Now why it is called TQFP? Because as you can see on the diagram, quad means it has 4 sides. So we have pins from all the 4 sides. It's been thin because it's flat, so that it can be easily mounted on the board. That's why it's called Thin Quad Flat Package. Now this type of package is used in industrial purposes, as the soldering of this particular pins are a little difficult, which we cannot perform with the normal ones. So we need to use different machineries for this one. And for PDIP package, which was shown earlier, have a through hole kind of mounting, which we can do with the hand solder. So that's how our packages will look like. Now we will look at the pin diagram of our microcontroller. So as you can see in the slide, this is the pin diagram of our microcontroller. Now in our hardware we have connected PDIP package of controller. So we have only 28 pins, which are these 28 pins of our controller. Now in order to do a programming of this microcontroller, what ATmega has done, they have divided this first of all into 3 different groups, named as B, C and D. So for this, the B port have 8 different pins, starting from PB0, which you can see as a pin number 14. Then you have PB1, 2, 3, 4, 5, 6 and 7. So in total for port B they have given 8 different pins of the microcontroller. So when we will be doing the programming of this controller, instead of writing as pin number 14, we will be writing as PB0. This is just to make the programmer to program the memory or to write the software in a very sophisticated way, or you can say very easy way. Similarly, for C also we have 7 different pins, starting from PC0, then PC1, 2, 3, 4, 5, 6. So from 0 to 6 it will be total 7 pins. So 8 pins of PB, or you can say port B, 7 pins of port C. And the third group which we have is for port D, again starting from 0, which we have PD0, PD1, PD2, PD3, PD4, PD5, PD6 and PD7. So in total we have 8 different pins of PD. For B we have 8, for C we have 7 and plus D we have 8. So in total we have 23 pins for this microcontroller, which can be used as an input pin or an output pin to the controller. Now what do you mean by an input pin? Input pin means you can connect different inputs to the controller, such as sensors. Like we can connect different sensors such as infrared sensors, temperature sensors, pressure sensors, sound sensors to that particular input pins, or you can say any of these 23 pins. Now output pins means the devices we can connect to the output of that particular pins, such as motors. Now as we know, there are 28 pins, out of which 23 pins can be used as an input or output pins. What about the remaining 5? Now you can see there is pin number 7, which is used as a VCC. Basically VCC is your power supply, and normally all the microcontrollers works on 5 volt DC supply. So we will be connecting the power to this particular VCC. So that would be a plus of your power supply, and this will be a minus, which is your ground. Now there are another 3 different pins, which is pin number 20, 21 and 22 as A VCC, A reference and ground. Now these 3 pins are also used for power for performing ADC operations. ADC means analog to digital conversions. So we need, whenever we want to convert an analog value into a digital value, we need to give certain voltages on this particular pins of our microcontroller. So this makes up this 3 plus 2 are our power pins plus 23 input output pins. That makes us 28 pins of our microcontroller. Now as you can see, along with these port names, we also have some names written on the brackets. This is nothing but the dual functionality of that particular pin. That means pin number 1 can be called as PC6 or can be called as a reset. Now this reset pin is the same reset pin which we have seen in the hardware as a reset switch. So the internally that reset switch will be connected to this particular pin of our microcontroller, and the functionality of this pin is to reset the microcontroller. So whenever we press this particular reset switch, what happens? The microcontroller stops whatever it is doing and will start executing the program from the start. Now suppose my controller wants to communicate to different microcontrollers, or a series of microcontrollers. Then for that we need to have a transmitter pin by which we can send a data to another controllers. Also we need a receiver pin to receive the data. So to transmit the data from our microcontroller to another microcontroller, we have a TXD pin, which is called as transmitter pin. Similarly for receiving we have another pin called as receiver pin, which is RXD. Now as I told you that our microcontroller works on frequency, so we need to connect a crystal oscillator, which I have already shown you on the hardware board. So that particular oscillator will be connected at these 2 pins, which is crystal oscillator 1 and crystal oscillator 2. So these 2 pins are basically used for connecting your crystal oscillator. Now also for connecting our sensors to the microcontroller, as we know that sensors give us an analog output, we need to convert that analog into digital. So for that we use 6 different pins starting from ADC 0, 1, 2, 3, 4, 5. So these 6 pins can be used for analog to digital conversions. Now also there are some more features of microcontrollers such as timers, So for timers we use pins like PD4, or you can say T0, which is timer 0, T1, which is timer 1, this is AIN0, which is analog interrupt 0, this is AIN1, which is analog interrupt 1, ICP, which is intercommunication process 1, or you can say input comparison 1. Then we have also OC1, which is output comparison register. So these all registers are used for our timer peripherals. Now also sometimes we need to communicate with another microcontroller through a communication method called as SPI, or we can say serial peripheral communications. Or what we can say, like suppose I want to transfer my program from my system or a laptop to my microcontroller. So for that we need 4 pins of this microcontroller, and they are pin number 16, 17, 18 and 19 on what we call as slave select. Now pin number 16 is slave select, in order to select the slave which is being connected to our microcontroller. Pin number 17 is MOSI, which means master out slave in. Pin number 18 is MISO, which means master in slave out. And pin number 19 is SCK, which is serial clock. So these 4 pins, 1, 2, 3, 4, along with VCC and ground, makes up 6 different pins which are used for transferring the data from our microcontroller to the system, or from the system to our microcontroller. So this to and fro communication is done with the help of these 6 pins. Now also we have 2 more left, which is INT0, which stands for interrupt 0 and interrupt 1. This is basically if there is an occurrence of an external interrupt to a controller, that would be given to this particular pins. So this basically summarizes of all the pin explanations of our ATmega microcontrollers.